Okay, so you know how to find the area of a square, right? Easy. But what about the area of a shape like this? When you've got these complex curves, basic geometry it doesn't work. So today we're going to build a calculus toolkit that lets us find the exact area of literally any shape you can possibly graph. And that is the big question, right? Geometry gives us these neat little formulas for predictable shapes. But for the area that's trapped between two curves, there's no simple length times width. To crack this, we need a whole new way of thinking. So let's dive in and see how it's done. So here's our game plan. We're going to build this toolkit piece by piece. First up, we'll get a handle on the problem itself. Then we'll add our two essential tools, the vertical slice and the horizontal slice. And finally, the most important part, learning when to use which tool for the job.
All right, let's get into it. Section 1, the curvy area problem. The thing is, when you're looking at an area bounded by functions on a graph, you can't just pull out a simple formula. You need a method, a system that works every time. And that method, well, that's the whole idea behind integral calculus.
And here's the big secret, boiled down. The solution isn't some crazy complex formula. It's a method, slicing and summing. Instead of trying to measure this whole weird shape at once, we're going to slice it up into an infinite number of super simple shapes, rectangles, and then just add them all up. That's really it. Slice them up, add them up.
Okay, time to grab our first tool from the kit. This is the vertical slice method. I like to call it the upper minus lower approach. And honestly, it's pretty much exactly what it sounds like, and it is incredibly powerful. This picture just says it all, doesn't it? Imagine filling that area between the two curves, f of x and g of x, with an infinite number of paper-thin vertical rectangles. Now, the height of any one of those little rectangles is just the value of the top curve minus the value of the bottom curve. Our job is to just add them all together.
And here's how we translate that picture into math. Don't let the symbols freak you out. That big S-looking thing is the integral sign. It just means sum up. What are we summing up? The heights of the rectangles. That's the upper function, f of x, minus the lower function, g of x. And we do this for every single tiny vertical slice, which we call dx. See? Upper minus lower. That's the entire formula, right there. Okay, theory is one thing, but let's actually put this tool to work on a real problem from our source material. So we want to find the area between the line y equals x plus 6 and the parabola y equals x squared, specifically from x equals 0 to x equals 2. Okay, step 1. Look at the graph. The line is clearly on top. That's our upper function. The parabola is on the bottom. That's our lower. So we set up our integral, the sum of upper minus lower. That's x plus 6 minus x squared, and we're summing from 0 to 2. Now all we got to do is solve it.
And when we apply the rules of integration, which is really just the reverse of finding a derivative, we solve it and boom, we get our answer. The exact area trapped between that line and that curve is 34/3. We just got a precise answer for a really complex shape. That's the power of this tool.
And you know what? This tool is super versatile. The source material shows it works just as well for other kinds of curves, like a square root function and a different parabola. The process is exactly the same. Find your upper, find your lower, and integrate. The method never changes. Okay, but what happens when it's not so simple? What if the upper and lower functions actually switch places partway through? Or what if the curves are defined in terms of y instead of x? Sometimes slicing things vertically can get, well, complicated. We're going to need another option in our toolkit. Just look at this comparison. On the left, a vertical slice is perfect. The upper and lower functions are always the same. No problem. But now look at the shape on the right. If you try to use a vertical slice there, oh man. Your lower function would sometimes be one curve, and then it would switch to the other. That's a huge headache. There has to be a better way. And guess what? There is a better way. Say hello to our second tool, the horizontal slice. If upper minus lower was our mantra before, our new one is right minus left. The big idea here is to just kind of tilt your head 90 degrees. Instead of thinking about tall, skinny, vertical rectangles, we're now imagining short, wide, horizontal ones. We're summing up an infinite number of these paper-thin, horizontal rectangles. And this time, we care about their width. And the formula reflects this change perfectly. We're still summing things up, but now we're summing up the widths. That's the function on the right minus the function on the left. And And this is super important. Notice that our slices are now dy. They're tiny slices of the y-axis. This means our functions have to be written in terms of y, like x equals something. So let's use this new tool on that tricky shape from before. Our functions are x equals y plus 2 and x equals y squared. See how easy this is now? The line is always on the right and the parabola is always on the left. No more confusion. So we set up the integral, right minus left, and this time we integrate with respect to y, from y equals -1 up to y equals 2. We run the integration and we get this nice clean answer 9/2 or 4.5. How cool is that? By simply choosing the right tool for the job, the horizontal slice, we turned a really messy problem into a totally straightforward one. That's why you need a whole toolkit.
So now we have our two main tools. The final skill, the real pro move, is knowing which one to pick. Let's break it down into a super simple guide.
Think of this slide as your cheat sheet. Is it easy to spot one consistent upper and one lower function? Go with a vertical slice. Are your functions already solved for x, or does it just make more sense to think in terms of right and left? Go horizontal. It's all about choosing the path of least resistance. And that's really the heart of it, you know? The real power isn't just in memorizing a formula. It's about developing that strategic thinking, looking at a problem and knowing exactly which tool from your kit is perfectly designed to solve it.
So let's just take a second to recap what we did. We started with what seemed like an impossible problem, finding the area of a shape with curvy, unpredictable sides, and we built a complete system to solve it. You now have the fundamental tools to measure literally any 2D area, no matter how wild it looks.
So slicing a 2D area into infinite little 1D lines gives you area. What do you think happens when you take a 3D shape and slice it into infinite 2D disks? That's right, you get volume. And that, well, that's a story for our next explainer.